While much of the world was wrapping presents and watching Christmas movies on December 24, 2024 NASA did something that scientists had called physically impossible for decades. A spacecraft about the size of a car flew straight into the sun's atmosphere. Not near the sun, not around the sun, but into it. And it did this at almost 692,000 kilometers per hour. This is the fastest object the human species has ever built. At that speed, you could cross Brazil from end to end in just a few seconds. And then, the moment it disappeared behind the sun, all contact went silent. The team in the control room had no way of knowing if the spacecraft was still alive. All they could do was wait. This is the story of how humanity literally touched a star, and of what we found inside when we touched it. Most people think the sun is dangerous for a simple reason. It's hot, and it is. Its surface reaches about 5,500 degrees Celsius. That's already hotter than almost anyone can really imagine. But here's where it gets weird. The surface isn't the dangerous part. The dangerous part is the corona. The corona is the sun's outer atmosphere, a gigantic and invisible envelope of plasma that extends for millions of kilometers in all directions. And the corona isn't just hot, it's, in an almost offensive way, way too hot. While the surface of the sun is around 5,500 degrees Celsius, the corona reaches temperatures between 1 and 3 million degrees Celsius, up to 300 times hotter than the surface just below it. Stop everything and think about that for a second. Because that violates what everyone learned about how heat works. Moving away from a campfire makes you colder. When you move away, it gets colder. It's fundamental in thermodynamics. And the sun does exactly the opposite. As you move away from the surface and enter the corona, the temperature skyrockets. Physicists call this the coronal heating problem. And for more than 80 years, it was one of the greatest unsolved mysteries in all of astrophysics. But this isn't just an academic curiosity, because it's from this corona that the solar wind is born. A continuous stream of charged particles, which the sun spits out in all directions at speeds between 200 and 500 kilometers per second. This stream reaches the Earth. It hits our magnetic field. And when it hits hard enough, it creates geomagnetic storms that can knock out satellites, scramble GPS, cut off radio communications, and overload entire power grids. So understanding the sun is not just an exercise in curiosity. It's about protecting the infrastructure that civilization relies on, and modern life runs on it every single day. Before we get to the mission itself, there's a story you need to hear. Because the spacecraft was named after a living person, and that almost never happens. In 1958, a young astrophysicist named Eugene sat down and wrote an article arguing that the sun constantly emits a stream of charged particles that flows outward, passing through the entire solar system. He called this the solar wind. When he sent the article to an important scientific journal, the editors sent it back. The reviewer, a respected scientist, wrote that the work contradicted established physics and should not be published. Parker appealed. The article was only published after the intervention of the editor-in-chief, Subramanian Chandrasekhar, who would win the Nobel Prize in Physics years later. 2 years later, measurements taken by spacecraft confirmed that Parker was completely right. The solar wind existed exactly as he described. And in the following decades, Eugene Parker became one of the central figures in solar science. So, when NASA prepared a mission to enter the sun's atmosphere, it decided to do something it had never done in its entire history. Name the spacecraft after a living person. Parker was 91 years old on the day of the launch. He was standing at the base in Florida, watching the rocket with his name soar into the sky. He died in 2022 at the age of 94, having lived long enough to see his probe transform our understanding of the star he studied his whole life. That detail matters because it shows just how significant this mission was, even before it took off. And now the problem that kept physicists and aerospace engineers up at night for decades. How do you build a spacecraft that can operate inside the atmosphere of a star? The side of Parker that faces the sun reaches about 1,370 degrees Celsius during its closest approaches. That's hotter than lava. It's hot enough to melt steel, aluminum, titanium, and almost any other metal you can think of. And even so, the scientific instruments sitting right behind the heat shield operate at about 29 degrees Celsius room temperature through a piece of material that's only about 11 centimeters thick. The solution is one of the most elegant pieces of engineering that NASA has ever produced. The shield, officially called the Thermal Protection System, is made of two panels of carbon composite surrounding a core of carbon foam. And that foam is 97% air. It's insanely light, insanely strong, and one of the most efficient thermal insulators ever flown in space. The side facing the sun is still covered with a special white paint that reflects most of the incoming light instead of absorbing it. But here's the part that surprises almost everyone. The corona is 1,000,000 degrees. And even so, the spacecraft doesn't burn up. Why? Because temperature and heat are not the same thing. Temperature describes how fast individual particles are moving. Heat describes how much energy those particles actually transfer when they collide with something. The corona is incredibly hot, but it's also almost a perfect vacuum. There are very few particles per cubic centimeter. So, while each particle travels with enormous energy, there are so few of them that the actual heat load reaching the shield remains manageable. The spacecraft doesn't survive by swimming in a 1,000,000-degree bath. It survives because an almost total vacuum at 1,000,000 degrees ends up being something that a well-designed carbon shield can handle. Few people discuss another major engineering challenge. At almost 692,000 kilometers per hour, the thermal forces trying to tear the spacecraft apart are immense. The engineers installed flexible joints that allow the structure to give and bend in the face of these forces instead of resisting, staying rigid and breaking. The spacecraft was literally designed to bend, not to snap. Parker took off in August 2018, but it didn't fly straight to the sun. It couldn't. The gravitational geometry of the solar system makes a direct approach practically impossible. A spacecraft launched from Earth carries too much orbital velocity. It would simply fly straight past, ending up in a wider orbit instead of falling toward the sun. To solve this, NASA used a technique called gravitational assist, basically using the gravity of another planet as a slingshot to redirect and slow down the spacecraft. And the chosen planet was Venus. Over the course of 6 years, Parker skimmed past Venus 7 times. Each flyby used the planet's gravity to take a bit of orbital speed away and tighten the spacecraft's orbit closer and closer to the sun, like slowly reeling in a fishing line. With each orbit, the spacecraft set a new record for closest approach, a new perihelion, before moving away again and then falling back in, closer than the previous time. And during those 6 years of increasingly tighter orbits, it was already making discoveries. It discovered that the solar wind near the sun is much more complex and turbulent than anyone expected. It detected zigzag reversals in the sun's magnetic field, structures that scientists nicknamed switchbacks, which appeared in much greater numbers than expected and seemed to play a central role in accelerating solar particles to impressive speeds. It crossed giant coronal mass ejections, those huge explosions of solar plasma, and measured each one from the inside for the first time in history. The last flyby of Venus was in November 2024. After that, there was nothing left to do. Just wait for Christmas to come. On the morning of December 24, 2024, the team at the Johns Hopkins Applied Physics Laboratory in Maryland was not celebrating the holiday. They were sitting at the consoles looking at telemetry data, waiting for their spacecraft to disappear. As Parker descended toward its closest approach, it entered a communication blackout zone, a region so close to the sun that the electromagnetic radiation from the corona completely swallows any radio signal the spacecraft tries to transmit. The team knew this was coming. They had planned for it. But knowing something in your head and actually experiencing it are very different things. At some point on that Christmas Eve, the spacecraft, a machine they had spent more than a decade designing, building, and caring for over 6 years of ever closer orbits, went silent, completely out of reach. No telemetry, no signal, nothing. And there it was, about 6.1 million kilometers from the surface of the sun, traveling at 692,000 kilometers per hour, flying on autopilot through the atmosphere of a star with no ability to receive new commands or send any data back. Just so you know, Mercury, the closest planet to the sun, never gets closer than 45 million kilometers from the solar surface. Parker was more than 7 times closer to the sun than Mercury ever gets. On the night of December 26, 2 days after the closest approach, the operations center received what it had been waiting for. Beacon signal, just a simple radio transmission indicating the spacecraft's health status. It was as if it was saying, "I'm here, I'm operational, everything is working normally." They say the room erupted. Engineers who spent years of their careers on that mission were openly moved. When the complete scientific data began downloading to Earth in early January 2025, researchers finally had something they had never had before: a detailed view of the sun's corona from the inside. Not from a telescope pointed from afar, millions of kilometers away, but from within it. And the data immediately began to answer questions that had been open for decades. The spacecraft's wide-field camera, the probe's imaging instrument, captured the birth of the solar wind. You could see the streams of magnetized plasma breaking away from the corona, accelerating outward, organizing themselves into the patterns that later reach Earth. Scientists describe this as finally being able to observe a river at its source, after decades of only being able to look at it hundreds of kilometers downstream. Suddenly, the entire dynamics of how solar weather forms became visible in real time. The data also captured something that previously only existed as a theoretical prediction, a phenomenon that NASA scientists are calling the U-turn of the solar wind. When the sun releases a coronal mass ejection, one of those huge explosions of magnetized plasma, not all of the material escapes into space. Part of it curves back toward the sun, pulled by the star's own magnetic field, altering the corona and influencing the path of the next ejection. Parker filmed this directly up close, at a level of detail that no one had seen before. Understanding this feedback mechanism is crucial to improving space weather forecasting, because it helps explain why some solar storms are much more violent than others. There's also the mystery of coronal heating. The preliminary data from the approach point to those switchbacks, those zigzag magnetic reversals, as one of the main mechanisms by which energy is transferred from the surface of the sun to the corona, heating it to millions of degrees. It's not just one process. It's a complex combination of magnetic reconnection events and turbulent wave activity. And Parker's giving scientists the resolution they needed to finally map this properly. 80 years of mystery may be close to an answer. Parker kept making close approaches throughout 2025, each time matching the record of 6.1 million kilometers from the surface in the speed record. The sun is now near the peak of its 11-year activity cycle, which means solar storms are more frequent and more intense. And Parker's collecting data right in the middle of it. But take a step back and think about why this really matters in practical terms. Today, every time a big solar storm approaches Earth, satellite operators have between 15 minutes and just a few hours of warning. That's barely enough time to put satellites into safe mode, let alone protect major power infrastructures. A strong enough storm, comparable to the Carrington event of 1859, could trigger cascading failures in the power grids of entire continents. Some estimates suggest that recovery would take months or years, at a cost that would make almost any other natural disaster in history seem small. And Brazil has even more reason to pay attention to this. Right above us, there's a weak spot in Earth's magnetic shield. Scientists call it the South Atlantic Anomaly. It's a region centered over Brazil and the South Atlantic, where the planet's magnetic field is up to 30% weaker than the global average. And the magnetic field is exactly the shield that keeps away the charged particles that the sun spits in our direction. Where this shield gets thinner, the particles can get closer to the surface. That's why the anomaly got a nickname among space engineers, the Bermuda Triangle of space. When a satellite crosses this region, it enters a much more intense radiation zone. Several satellites turn off sensitive instruments while passing over Brazil. The Hubble telescope doesn't collect data there, and the astronauts on the International Space Station, who cross the anomaly on every orbit, don't do spacewalks while they're over it. I want to be fair since your common sense is correct. That doesn't mean that you, standing on the ground, are getting bathed in radiation. The air and distance still protect you down there. The effect is felt up there in orbit, exactly where the technology your life depends on resides. Your cell phone's GPS, the weather forecast, satellite TV, the signal that makes your card work in the machine. When a solar storm energizes the radiation belts around the Earth, it's right here, over South America, that they are already lower. In other words, the infrastructure that passes over Brazil is among the most exposed in the world to this type of event. And the anomaly, according to the most recent measurements from the European Space Agency, is not stationary. It has been growing and even splitting into two over the past decade. That's why a probe diving into the sun to understand space weather at its source isn't a distant topic for those who live here. It may matter more to us than to most of the planet. The data that Parker's gathering, close to the sun, to see how the solar wind forms, how coronal mass ejections behave at their origin, how magnetic structures evolve before they erupt. They are the foundation for building real warning systems. Instead of 15 minutes of warning, we could one day be talking about days. And that difference isn't just scientifically interesting. It could protect trillions in infrastructure and millions of people who depend on it every day. On December 24, 2024, a machine built by human hands flew into the atmosphere of a star. It survived temperatures that would vaporize any ordinary material. It moved faster than anything we've ever made. And it came back with data that's already rewriting textbooks. I admit I see the sun differently after learning this. We grow up thinking the sun is a constant ball of fire, always there, always the same. And it's actually a living, turbulent thing with its own weather that blows in our direction all the time. And for the first time, we're learning to predict it instead of just suffering from it. For thousands of years, every culture that looked at the sun treated it as something untouchable. God, mystery, a force beyond human reach. NASA reached it anyway. And what Parker found inside the sun won't just change the way we do science, it will change how well we can protect the civilization that took so long to build.